Good afternoon, everyone. My name is Gillian Molino, and I'm very happy to present to you in a virtual way our paper, which is titled OFDM-based Spatial Data Focusing for High-Resolution Two-Dimensional Wireless Geocasting. Now, this presentation will consist of a couple parts. The first one being an introduction, explaining what exactly geocasting is and what spatial data focusing is and how spatial data focusing can be used to ensure geocasting. Secondly, I will introduce the free space system model of spatial data focusing. And then in sections 3 and 4, I will assess how it is possible to modify the focusing direction to any arbitrary location, and how to do sidelobe mitigation, ensuring essentially the uniqueness of our focus or target point. Then I will discuss the simulations and the small performance evaluation to finish with the conclusions and perspectives. Now, geocasting is defined as a location-based multicasting scheme, which means that information is transmitted in such a way that it is only available in spatially confined regions and is unavailable to users not inside these areas. Now, this has a lot of applications. Think, for example, of IoT and smart city environments where a large amount of wireless devices could benefit from receiving location relevant or location contextualized information. Now, the idea of geocasting is that it does not require the localization of users and hence respects their privacy when it comes to location, of course. Now, in order to perform geocasting wirelessly, spatial focusing capabilities are required at the base station, which can be done very typically by beamforming, which is a spatial power focusing technique, or in the domain of physical layer security, directional modulation can be used, or as I would like to introduce in this presentation, spatial data focusing. Now, I would like to first explain the conceptual difference between spatial data focusing here on the right and beamforming here on the left. Beamforming, as is very well known, is a power focusing technique that focuses power to the intended locations by exploiting constructive and destructive interference between the different antennas in an array. Now, beamforming has a limited precision, meaning that large arrays are required to obtain accurate focusing to a certain position. Spatial data focusing, on the other hand, does not manipulate the radiation pattern of the array. Instead, it focuses by creating a location-dependent symbol distortion such that information can only be, or the symbols can only be decoded in the predetermined areas. And the benefit of using spatial data focusing over beamforming will be that there is an increased precision with a reduced array size. Now, the free space system model, now spatial data focusing always works by transmitting a certain data sequence in a distributed way over different antennas. This can be done, as was previously already investigated, by using time slots and transmitting each time slot over a different antenna. This is time-based spatial data focusing. However, for OFDM-based spatial data focusing, an OFDM block SQ is transmitted over n different antennas using as a resource the Q subcarriers that are used in OFDM. Specifically, what is done is that n antenna-specific OFDM blocks Xi are defined, and the OFDM blocks Xi carry on those subcarriers Q that are part of the subcarrier set Qi that was assigned to this antenna. They carry the same information as SQ, and they don't contain any information on the other subcarriers, such that the OFDM block SQ is transmitted in its totality over all n different channels. Now, of course, each channel is characterized by a unique propagation delay, and on top of that, different symbols are also transmitted on different subcarriers. This means that the channel transfer function for a particular system, for a particular symbol, is characterized by a certain subcarrier Q and a certain delay tau I, characterized by depending on the antenna that is transmitted on. And it is these two degrees of freedom that we will exploit in order to focus. Now, in a free space scenario, we will assume that the channel amplitude and the channel phase, so A and phi respectively, are identical for all channels. Now, essential for spatial data focusing is that channel estimation is performed only on a set of predetermined reference subcarriers and their corresponding channels. This information, this estimation, will then be copied and also used for the estimation or the equalization of all other subcarriers. So essentially, we define our spatial data focusing channel estimation as the estimation of the reference channel for all subcarriers that are part of the reference subcarrier set. However, we also define it on the subcarriers that are not part of the reference subcarrier set as also an estimation of the reference channel on QREF, subcarrier QREF, which is the previous subcarrier on which we have an estimation of the channel. The consequence of this is that upon equalization, there will be a residual phase shift left on in the equalized symbols, which is angle and distance dependent. The angle dependence comes from this first term, which is a consequence of the different propagation delays of each channel over which symbols are transmitted. And the distance dependent term comes from the fact that different symbols are transmitted on a different subcarrier. Now, the idea is that this residual phase shift is zero only in restricted regions where the bit error rate will be zero as a consequence and communication will be possible. And that the phase shifts, the residual phase shifts are non-zero in all other locations, such that communication will not be possible. Now, one important question that one can ask himself is, how can I target the exact location that I want? So for this, imagine that we want to create a location or a spot, a focus point of low bit error rate at the polar coordinates of d steer, the distance between base station and receiver, and theta steer, the azimuth angle of the receiver with respect to the broadside direction. Now, to do this, we introduce a pre-distortion phase shift on each channel, on this, to the symbols on each channel I and each subcarrier Q. This one is visualized here in red on the slides. And as a consequence, the equalized received symbols will contain, on top of the two phase shifts that it already had, it will contain a phase shift which is determined by this steering phase of the ith channel and the qth subcarrier, minus, of course, the steering phase of the reference channel and the reference subcarrier. Now, by expressing that this phase shift, this residual phase shift should be zero at the intended steering point, one can find an expression for the steering phase that should be added to each channel. This one is, of course, dependent on the subcarrier that is used on the difference in channel delta I between the channel that is equalized and the reference channel. Of course, the steering coordinates theta steer and d steer, and then, of course, the difference in subcarrier with respect to the reference subcarrier. Secondly, it is important that we are able to ensure uniqueness of the focus area, that there is no second area present where data could also be retrieved. And we need to ensure uniqueness both in the radial domain as well as in the angle domain. So for the radial uniqueness, if we look at the radial solutions of the expression stating that the residual phase shift should be zero, one can see that we find a solution of this form. Now, the important conclusion to make here is that there is an integer k present in this expression, which makes it so that the solutions to this equation are periodic in the radial domain with a periodicity of c divided by bc, respectively the speed of light and the subcarrier bandwidth. Now, this in combination with the fact that the radial domain is infinite makes it so that uniqueness is impossible to assure in theory. However, in practice, if we can satisfy two conditions, the first one being that there is no solution in the range from 0 until the steering point, meaning that the periodicity should be larger than the steering range. And secondly, that the solutions that are larger or that are beyond the steering point should occur at ranges where the attenuation is sufficient to not be able to retrieve the symbols, meaning that, again, the periodicity should be larger than the attenuation range minus the steering range. And if both of these conditions are satisfied, then practical uniqueness in the radial domain is ensured. In short, one can say that when designing a system, the subcarrier bandwidth should be chosen as such that it is smaller than the minimum of these two expressions. Secondly, we have the uniqueness in the angular domain, which follows from the angular solutions of stating that the residual phase shift on the received symbols should be 0. It is the solution of an inverse sine, and by stating that there can only be one solution in the range from -pi divided by 2 to pi divided by 2, one finds a condition on the antenna spacing B, stating that it should be smaller than a certain fraction of the carrier wavelength, a fraction which is, of course, determined by the steering angle that is chosen. If we have a look then at some of the simulations, so we did a simulation here where the steering range is at 250 meters and an azimuth angle of 20 degrees, which is given in the figure by a red dot. We can see that there is a blue region, which signifies a low bit error rate, and hence communication is possible, that is centered exclusively around this target point. So confirming that we are indeed able to steer towards the desired location without having any other locations of low bit error rate. We can also look at an intersection of this figure at the steering range and also at the steering angle. So at the steering range, so having on the y-axis the bit error rate and on the x-axis the azimuth position of the receiver, we can compare the performance of OFDM-based spatial data focusing to time-based spatial data focusing. And we can see that there is no trade-off in terms of angular selectivity. On top of that, we see that we still have a considerable increase in spatial selectivity when we compare spatial data focusing to beamforming. Secondly, we can look at an intersection of our bit error rate pattern at the steering angle, and we see that the radial accuracy of focusing is dependent on the subcarrier bandwidth, as we said, and that when we satisfy the conditions that avoid radial side lobes, we can achieve a radial focusing resolutions of approximately 20 meters. In conclusion, by using OFDM-based spatial data focusing, two-dimensional data focusing is possible, and when compared to time-based spatial data focusing and beamforming, both of them who are restricted to angular focusing only, we have thus created an additional geocasting flexibility thanks to the radial focusing aspect. We do not have any trade-off with respect to angular selectivity compared to time-based spatial data focusing, and we also maintain the increased resolution or the resolution improvement over beamforming that was already present for time-based spatial data focusing. On top of that, we were able to define design rules that guarantee beam steering to any arbitrary position, and also side lobe mitigation that ensures the uniqueness of our focus location. And with these final remarks, I would like to conclude the presentation and thank you all for your attention.